All the Python source code for this lesson is available for download. See video description. Welcome to our guide on Convolutional Neural Networks, CNN, image classification. For this example, we will use a model that has a total number of layers equals 273, as you can see in the movie below. CNN are typically used for image data as they excel in capturing spatial information. Convolutional neural networks are a specialized kind of neural network designed for processing grid-like data, such as an image, which has a spatial relationship. CNNs have their neurons arranged more like those in front of a human eye, rather than in neat rows and columns. CNNs possess two key features that make them unique and particularly suited for image processing tasks: local receptive fields and shared weights. Local receptive fields allow CNNs to focus on small input regions, enabling them to identify local features like edges and corners. Shared weights, on the other hand, allow CNNs to recognize the same feature regardless of its position in the input, giving CNNs their characteristic translation invariance property. Convolution is a mathematical operation that forms the backbone of a convolutional neural network. In the context of a CNN, convolution involves taking a filter, also known as a kernel, and sliding it over the input image to produce a feature map or convolved feature. This operation allows the network to learn and identify spatial hierarchies or patterns in the input data. Filters in a CNN are small matrices of weights that are learned during the training process. Each filter is designed to detect a specific feature in the input data, such as edges, corners, or more complex shapes in higher layers of the network. To perform convolution, the filter is slid over the input image and at each position. A dot product is computed between the filter and the part of the image it is currently on. This results in a single value that represents the presence of the feature the filter is designed to detect. The process is repeated for every position on the input image, resulting in a feature map that represents where and to what extent the feature appears in the image. Stride and padding are two essential concepts in convolution. The stride refers to the number of pixels by which the filter is shifted at each step of the convolution process. Padding involves adding extra pixels around the input image to ensure that the filter fits properly at the edges. Both stride and padding can be adjusted to control the size of the output feature maps and the level of detail they capture. Convolution allows a CNN to learn complex patterns in the input data using relatively few parameters. By sharing weights across the input, the network can recognize the same feature regardless of its position in the image, giving CNNs their characteristic property of translation invariance. This makes CNNs particularly effective for tasks involving images, where the same feature can appear in different positions. A typical convolutional neural network consists of an input layer, multiple hidden layers, and an output layer. The hidden layers often include a series of convolutional layers, followed by activation functions, pooling layers, fully connected layers, and normalization layers. Each of these layers plays a specific role in the processing and transformation of input data. Convolutional layers are the core building blocks of a CNN. They perform a convolution operation on the input data and pass the result to the next layer. The purpose of the convolutional layers is to extract high-level features from the input data, such as edges, corners, and other relevant attributes. Following each convolutional layer, an activation function is applied to introduce non-linearity into the model. This allows the network to learn complex patterns and relationships in the data. Commonly used activation functions in CNNs include the rectified linear unit, ReLU, sigmoid, and hyperbolic tangent, tanh. Pooling layers are used to reduce the spatial dimensions, width and height, of the input volume. This serves to decrease the computational complexity, control overfitting, and consolidate the features extracted by the convolutional layers. Two common types of pooling are max pooling and average pooling. Fully connected layers connect every neuron in one layer to every neuron in the next layer. In a CNN, Fully connected layers often come after several convolutional and pooling layers. And they serve to interpret the features extracted by the convolutional part of the network. The final fully connected layer uses a softmax activation function to output a probability distribution over the classes. Normalization layers, such as batch normalization and local response normalization, LRN, are used to standardize the inputs to a layer for each mini-batch. This has the effect of stabilizing the learning process and dramatically reducing the number of training epochs required to train deep networks. The combination of these layers forms a CNN architecture. The exact architecture can vary widely depending on the specific application. But all CNNs follow the general pattern of alternating convolutional layers, with activation functions, and pooling layers, followed by fully connected layers. For this example, we will use a model that has a total number of layers equals 273 grouped in these categories. Input layer, 1. Rescaling, 1. Conva 2D, 49. Batch normalization, 46. TFOpLambda, 58. ReLU, 48. Multiply, 29. Depthwise Conva 2D, 15. Add, 10. Zero padding 2D, 4. Global average pooling 2D, 9. Dropout, 1. Flatten, 1. Activation, 1. Activation functions for some of the layer types. Conva 2D, linear, 49. Depthwise Conva 2D, linear, 15. Activation, softmax, 1. Total number of layers equals 273. Let S detail each layer type. After the layer there is a counter representing the number of times it was used in this model. 1. Input layer, 1. The input layer is the first layer in a Keras model, responsible for defining the input shape and data type of the model S inputs. It serves as the entry point for the data into the model. It acts as a placeholder for the actual input data during training, evaluation, or prediction. The input layer doesn't have any trainable parameters since it is not involved in actual computations. 2. Rescaling, 1. The rescaling layer is used to perform data rescaling or normalization in the input pipeline of a neural network model. It scales the input data by a specified factor and shifts it by a specified offset. For example, scale equals 1.0255.0 scales the input data by dividing it by 255, which is typical for image data to bring the pixel values within the range of 0 to 1. The rescaling layer doesn't have any trainable parameters since it performs a simple scaling operation on the input data. 3. Conva 2D, 49. The Conva 2D layer in Keras performs a two-dimensional convolution operation on the input data. It applies a set of filters to the input feature maps and performs element-wise multiplications and summations to produce the output feature maps. The main purpose of the Conva 2D layer is to extract local spatial patterns or features from the input data. It applies convolutional filters to capture important spatial relationships and hierarchies present in the input, which is especially useful for image processing tasks. The Conva 2D layer has trainable parameters, including the filter weights and biases, which are learned during the training process. These parameters capture the spatial patterns and features present in the input data. Each filter slides across the input feature maps, performing element-wise multiplications and summations. The resulting convolved feature maps are then passed through the activation function and forwarded to the next layer in the model. 4. Batch normalization, 46. The batch normalization layer is used to normalize the activations of a neural network by applying a transformation that maintains the mean activation close to 0 and the activation standard deviation close to 1. It operates on a mini batch of inputs and adjusts the activations based on the statistics of the current batch. It helps to stabilize and accelerate training by reducing internal covariate shift and reducing the dependence on the initialization of the network. The batch normalization layer has trainable parameters, including scale, offset, moving mean, and moving variance. 5. TFOpLambda, 58. The TFOpLambda layer allows you to integrate custom TensorFlow operations, ops, or functions into your Keras model. The TFOpLambda layer doesn't have any trainable parameters since it doesn't perform any computations on its own. It simply applies the provided TensorFlow function or operation to the input data. 6. ReLU, 48. The ReLU layer implements the rectified linear unit activation function, which is a commonly used activation function in neural networks. It applies an element-wise nonlinear activation to the input, setting all negative values to 0 and leaving positive values unchanged. The main purpose of the ReLU layer is to introduce nonlinearity into the model. By zeroing out negative values in the input, the ReLU activation function helps the network learn complex patterns and capture nonlinear relationships between the features. 7. Multiply, 29. The multiply layer performs element-wise multiplication between two input tensors of the same shape. It multiplies the corresponding elements from the input tensors to produce the output tensor. It allows the model to learn interactions or relationships between different features or representations. 8. Depthwise Conv 2D, 15. The depthwise Conv 2D layer is a depthwise separable convolution layer that performs separate convolutions on each input channel, depth, independently. It applies a different filter to each input channel and produces a set of output feature maps. The depthwise Conv 2D layer has trainable parameters, including the depthwise convolutional filters and biases. The number of parameters in the layer depends on the size of the filters, the number of input channels, and the depth multiplier. 9. Add, 10. The add layer performs element-wise addition between two or more input tensors of the same shape. It adds the corresponding elements from the input tensors to produce the output tensor. The add layer allows the model to learn additive interactions or relationships between features. 10. Zero padding 2D, 4. The zero padding 2D layer adds rows and columns of zeros around the input tensor. It increases the spatial dimensions of the input feature maps by padding them with zeros. The zero padding 2D layer is typically used to handle situations where the input size doesn't match the expected size for subsequent layers. 11. Global average pooling 2D, 9. The global average pooling 2D layer computes the average value for each channel of the input feature maps across all spatial dimensions. It reduces the spatial dimensions of the feature maps to a single value per channel. The global average pooling 2D layer is typically used as the final pooling layer before the fully connected layers or the output layer in a convolutional neural network. It converts the spatial feature maps into a fixed-length vector. It helps to summarize the spatial information of the feature maps, enabling the network to make predictions based on global context. 12. Dropout, 1. The dropout layer is a regularization technique that randomly sets a fraction of input units to 0 during training. It helps to prevent overfitting and improves the generalization ability of the model. By randomly dropping units, it forces the network to learn more robust and generalized representations that are not overly reliant on specific inputs. 13. Flatten, 1. The flatten layer flattens the input tensor into a one-dimensional array. It reshapes the input from a multi-dimensional tensor into a single vector, while preserving the total number of elements. The flatten layer is typically used as a bridge between convolutional or recurrent layers and fully connected layers. It enables the transition from spatial or sequential representations to a flat vector representation suitable for dense layers. 14. Activation, 1. The activation layer applies an element-wise activation function to the input tensor. It introduces non-linearity into the network and helps to capture complex relationships between features. It is used to introduce non-linearities such as ReLU, sigmoid, or softmax activations to transform the input tensor. 15. Activation, softmax, 1. The softmax function takes a vector of real numbers as input and transforms it into a probability distribution over multiple classes. It normalizes the input values and ensures that the resulting probabilities sum up to 1. It normalizes the input values, making them interpretable as class probabilities.